Double pendulums and the three-body problem are two examples of chaotic systems. A chaotic system basically means that very slight changes to the initial starting conditions will cause a vastly different trajectory, and these trajectories are either difficult or impossible to predict. After seeing these two systems in action, I felt that they had a lot of similarities, and I began to wonder how they overlap. In this project, we'll be constructing some novel scenarios that transition between double pendulums and the three-body problem, and we'll see what kinds of behaviors result from these hybrid setups. I've already spent some time with the three-body problem, and I found that this class of orbits called BHH orbits gives the most reliable results for periodic pathing, so that will be our starting place for these experiments. To recap, these orbits have some randomized starting conditions that follow these rules, and the planets have starting velocities that equate to net zero momentum. One characteristic of these orbits is that they have a rotational value, which you can see through the offset lines in these examples. With double pendulums, I saw a simulation of them depicted as angle graphs, and I wanted to try that out with these orbits. I graphed the angles between each pair of planets to see what would result, and this is what it looks like. The colors on the graph here don't make a lot of sense because the angles were produced by two planets, so in hindsight it would have been better to use blended colors. Okay, we have our starting point for the three-body problem, so let's go to the opposite end and take a look at double pendulums. I had some trouble getting this set up because the approaches I tried seemed to always make the system lose energy, but after looking up some other implementations online, I found this RK4 integration that worked pretty well. The challenge is, now that I have a basic setup, I'm not sure how to find periodic conditions for double pendulums. In my three-body project, I had some success running many parallel systems and just visually identifying periodicity, so let's give that a shot. Well, that's certainly a lot of pendulums, but I'm not seeing much. I think I need a more rigorous approach. Let's try out a pixel mapping system. In this method, a texture is designated, and each pixel on that texture represents one starting condition, and the conditions are minutely adjusted across each pixel. The pixels that show values with periodicity that last the longest are colored white, and the sooner the system falls out of periodicity, the darker the pixel is colored. You end up getting these interesting patterns like this. Just for fun, I also connected something similar to the BHH orbits using the values of the two variable planet masses, and I got this. I proceeded to make a method that reads the conditions of a given pixel, and I tried using some of those values. The results were fairly mixed. One of the challenges is defining periodicity and what that means for pendulums. In three-body systems, it's fairly simple to find something not periodic because if it isn't, one or more of the bodies will likely be slingshot off into infinity. So you can measure the distances between planets and end the simulation if a distance passes a certain threshold. I think the overhead of this pixel approach is distracting from the main goal of finding periodicity, so I'll leave that off to the side for this project. Let's just try to calculate simulations for the double pendulum and record the best results. It took a bit of experimenting, but the main method I went with was periodically recording the pendulum's angle and position, then checking if those positions were repeated. This ended up giving some pretty good results for periodicity. Here's a very clean periodic pattern that emerges in a number of different trials. And here are a few other interesting results. Some of the patterns have a gradual offset that reminds me of the BHH rotation value. Now that we have starting points for both three-body and double pendulums, where can we go from here? Let's take a moment to reflect on the similarities between both systems. Each system consists of 3 points. In the double pendulum, there is one fixed point and 2 mobile points, whereas a three-body system has 3 mobile points. Double pendulums have a universal downward gravity source, and three-body systems have 3 points of gravity centralized on the moving bodies. Lastly, the points of a pendulum are at a fixed distance, and a three-body system does not have fixed distances. So the 3 main things we can alter between the systems are the number of fixed points, the sources of gravity, and the allowed distances between given points. Let's proceed by modifying our double pendulum setup. We'll keep everything the same, except now the points themselves will exert gravity in addition to the universal downwards gravity. Sort of like there's a fourth distant body somewhere below that's pulling all of the other bodies. In my first couple experiments with this, I realized the lengths of the two arms need to be different, or else the bodies will come too close to one another and apply too much force. After some tweaking, this setup created some pretty interesting results. I tried a few trials with making one of the three bodies notably more massive than the others, and the diversity of the patterns that emerged really surprised me. At one point, it looked like an equilibrium had been reached for this system. However, even this state was eventually lost. Something I noticed is that it looked like the system as a whole was continually gaining energy. The other two systems produced similarly interesting results. Now, is there any chance we can find periodic orbits with these conditions? I modified my calculation script to answer this question. At first, the resulting orbits were quite chaotic, but after some tweaking, I found a couple patterns that resembled what we've already seen. I then drastically decreased the downwards gravity and found a few interesting results. This was the first one that really stood out as something unique. Here's another that was quite complex for how precise its periodicity is. And here's a nice cluster of unique examples. The asymmetry of the one on the right stood out to me here. So far, none of these examples have had any starting momentum, and when we add that in, we get some more geometric looking figures. We even get a sort of triangle shape, and the surprising thing about this one is that it oscillates between very precise periodicity and then slightly offset periodicity. Very strange. We found some good results for this system, so let's move on to what I'd consider to be the midpoint between double pendulums and three-body. I prefer to show this system second to last because I think the remaining system is more interesting. In this new system, we'll keep one fixed point and planetary gravity, we'll remove downwards gravity, and we'll have an elastic but not rigid force between two pairs of bodies. The elastic force is twofold. There's a threshold for both the maximum and minimum distance between two bodies. And, like a double pendulum, there are only the two connections between AB and BC. It wouldn't really be feasible to have only a pulling elastic force between the bodies because they would just collide, so I'm treating the connection like a flexible rod that can stretch and compress. This system definitely ended up being the most unstable, but it's also possible that I just didn't find a good range of starting conditions. After many trials, I did find one example that appears periodic, though it's not very exciting. With some more adjustments, this other pattern appeared in multiple instances. This orbit seems to be periodic with rotation, kind of like BHH, but the interesting thing is that this orbit actually exhibits retrograde or backwards motion. This was about the most interesting thing I could find for this system, so let's move on to the last. In the final system, we'll look at three moving bodies with elastic forces. Just to get an idea of how these elastic forces affect the setup, I started with the same kind of elastic bonds from the last scenario and placed them between each body pair. Strong elastic force creates chaos here, but with just slight pressure, I noticed that at least for the BHH orbits, the main difference is that it increases the rotational value of the system. I imagine the system as a whole is less stable, but I didn't extensively test this. I wanted to see if I could get some new orbit patterns, so I adjusted my testing calculator to account for the elastic forces and ran some trials. Also, to make things more similar to the double pendulum, I only kept the elastics for two body pairs. For the most part, these orbits seem like they could belong to the BHH class of orbits, but I did find some patterns that were new to me. I can't say I've seen a triangular orbit like this before. Among these trials, a few did stand out that were clearly only possible because of the elastic forces. I wanted to explore these further, and it seemed like increasing the minimum and maximum distances for the elastics further exaggerated the abnormal orbits. At first I just ended up with this, but after enough experimenting, I found some values that yielded more consistent results. Here's how they look. I'm reminded of sand dollars and other aquatic geometry when I look at these. There's a fairly consistent theme where two of the planets orbit in a close spiral, and then the third creates these separate spikes, but I find it interesting how even something as uniform as this can still have so much variation. People are interested in the three-body problem largely because it can and does exist in the universe. For these other systems I've created, I don't imagine that they have much application, but I do find enjoyment just in exploring odd ideas like this, and I'm happy that I was able to find some stable orbits across these weird and imaginary systems. There's a decent amount of math involved in creating simulations like this. And thanks to today's sponsor, Brilliant, you can get started in understanding what goes into problems like these. Brilliant is an online learning platform with thousands of interactive lessons on topics like programming, geometry, calculus, and more. Brilliant uses visual and interactive activities that help you learn by doing, and its wide collection of compact lessons make it easy to create a daily learning habit. The focus on active problem solving really helps ensure that you gain an understanding of a topic by encouraging critical thinking. To get started for free with Brilliant, just visit brilliant.org/woonuminal or check the link in the description or scan the QR code. They're also offering a 20% discount off of their premium annual subscription, which gives full daily access to all their content. Thank you all for watching the video, and a special thanks to Brilliant for sponsoring the video and to my supporters on Patreon. Until next time.